Imagine a still pond on a summer day. Now, picture a pebble dropping into its glassy surface. What happens? Ripples, of course. These ripples spread out from the point of impact, disturbing the calmness of the water. In the vast expanse of the cosmos, something similar occurs. Instead of water, it's the very fabric of spacetime that ripples. These ripples are not caused by pebbles but by some of the most powerful events in the universe. We call them gravitational waves. These waves are not like sound waves or light waves, they are fundamentally different. Gravitational waves are disturbances in spacetime itself. They travel at the speed of light, carrying information about the events that created them. These events are usually incredibly energetic and involve objects of immense density. Think colliding black holes, exploding stars, or even the echo of the Big Bang itself. Gravitational waves are a relatively new phenomenon in the world of astronomy. For centuries we have observed the universe using light, but light only tells part of the story. Gravitational waves offer a completely new way to observe and understand the cosmos. They are like a new sense, allowing us to perceive events that were previously invisible to us. Over a century ago, a young Albert Einstein revolutionized our understanding of gravity. His theory of general relativity proposed a radical idea. Gravity is not a force acting at a distance as Newton had thought. Instead, gravity is the curvature of spacetime caused by mass and energy. Einstein's theory was elegant and explained many astronomical observations that had puzzled scientists for years. But it also made a startling prediction. Accelerating massive objects should create ripples in spacetime. These ripples, he said, would spread out like waves, carrying energy away from the source. These were the gravitational waves. Einstein himself was uncertain whether these waves would ever be detected. They were predicted to be incredibly faint, even when produced by the most cataclysmic events. For decades, the search for gravitational waves remained a tantalizing but elusive quest. It was a challenge that would require cutting-edge technology and unwavering scientific dedication. To understand gravitational waves, we need to visualize spacetime. Imagine a vast, flexible sheet. This sheet represents the fabric of spacetime. Now place a bowling ball on the sheet. What happens? The ball creates a dip, a curvature in the sheet. This is similar to how massive objects like stars and planets warp the spacetime around them. Now, imagine two bowling balls orbiting each other on the sheet. As they move, they create ripples that spread out across the fabric. These ripples are analogous to gravitational waves. The more massive the objects and the faster they move, the stronger the waves they generate. When massive objects collide, they create an immense disturbance in spacetime. This disturbance sends out powerful gravitational waves that propagate through the universe at the speed of light. These waves carry with them encoded information about the objects that created them, their masses, their spins, and the moment of their final dramatic encounter. Section 4. LIGO, listening to the whispers of the cosmos. Detecting these incredibly faint ripples in spacetime was a scientific and engineering feat of extraordinary proportions. The instrument that finally achieved this breakthrough was the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two enormous L-shaped detectors located thousands of kilometers apart. Each arm of the L is a laser interferometer, a device that uses light to measure distance with incredible accuracy. When a gravitational wave passes through the Earth, it stretches and squeezes space-time ever so slightly. This stretching and squeezing affect the length of the arms of the LIGO detectors. The changes in length caused by gravitational waves are minuscule, far smaller than the width of a proton. Yet LIGO is sensitive enough to detect these changes. When a gravitational wave passes through, it creates a distinct pattern of light interference in the detectors. This pattern is LIGO's signal that a gravitational wave has arrived from the depths of space. Section 5. Unlocking Secrets. What gravitational waves reveal. The detection of gravitational waves has opened a new window into the universe. For the first time, we are able to observe objects and events that are invisible to traditional telescopes. This new era of gravitational wave astronomy is already providing us with groundbreaking discoveries. One of the most exciting discoveries was the detection of gravitational waves from the merger of two black holes. This event, billions of years in the making, sent ripples across the cosmos that were captured by the LIGO detectors. The signal provided direct evidence for the existence of black hole binaries, systems of two black holes locked in a deadly gravitational dance. Gravitational waves have also allowed us to observe the collision of neutron stars. These incredibly dense objects formed from the remnants of collapsed stars release a burst of gravitational waves and electromagnetic radiation when they merge. By studying these events, we are gaining insights into the origin of heavy elements like gold and platinum. Section 6. A new era of discovery. The future of gravitational wave astronomy. The future of gravitational wave astronomy is bright with promise. New and more sensitive detectors are being built around the world, creating a global network that will listen to the symphony of the cosmos. These detectors will allow us to probe deeper into the universe, observing events that are fainter and farther away. We are also developing space-based gravitational wave detectors such as the Laser Interferometer Space Antenna, or LISA. Free from the limitations of Earth-based observatories, LISA will be able to detect gravitational waves from sources that are currently inaccessible to us, such as supermassive black holes at the hearts of galaxies. Gravitational wave astronomy is still in its infancy, but it has already revolutionized our understanding of the universe. As we continue to explore this new frontier, we can expect even more groundbreaking discoveries in the years to come. Who knows what wonders await us, hidden in the symphony of spacetime?